you have read in plus 2 science or during plus 3 course. So in your pre-college or college days, what you have read in Gauss law, come prepared with that, and we'll discuss about Gauss law. So in this class, today's class, we'll discuss about Gauss law and see how much you have understood or whether you have come prepared or not with Gauss law. So that also we'll see. So to start Gauss law, we define first what is called electric flux. So with electric flux, that is the starting point. So what is flux? Flux is the rate of flow of an entity. When we say rate of flow of an entity, it does not mean it is time rate of flow. It can be any rate of flow, particularly if it is the entity is within a volume, so then it is the volumetric rate of flow. If the entity is passing an area, then it is the rate of flow for across area. So that will be the rate of flow. Rate of flow means how much of the entity is going out of a defined area or a defined portion in space. So that is what is flux. Now when this entity is electric field or electric field lines, then the flux is called electric flux. So the electric flux, the definition will be flow of electric field across an unit normal surface. So electric field, how it is flowing across a unit normal surface. Suppose there is a surface and the electric field is touching the surface, but the surface and electric field are not normal to each other. In that case, how are we going to find out the flux? The flux will be in that case. Suppose delta phi is the flux that is crossing an area delta A. As you know, area is a vector quantity. So delta phi will be the flux that is crossing an area which is obtained by a crossing of electric field and area delta A. Electric field is A, area is delta A. The normal of electric field and area, electric field crossing the area normally is the normal component of electric field with respect to area is E dot A. The the scalar product of E with A or the dot product of E with A gives us the normal component of electric field crossing the area delta A. Therefore, delta phi is equal to E dot delta A. Then you know the dot product rule A dot B is equal to AB cos theta. So E dot delta A will be E delta A cos theta, where theta is the angle between E and A. E is the electric field, so you know the direction of electric field. Similarly, A is the area, you know the area, direction of area is normal to its surface. Therefore, the angle between the electric field and normal to the surface of the area is theta. Then E dot delta A is equal to E delta A cos theta. Now, instead of this discrete area, if you consider an elemental area, so discrete area is you have an area which is, let us say, a rectangular area, so a small rectangular area. Instead of the surface is not uniform, surface is somehow distorted surface. If you have a distorted surface, then how you are going to find out the electric flux? If we have distorted surface, then what we do is we divide the surface into many elemental area, and over each elemental area we find out what is the uh, flux, then we integrate the flux for all the area, then we integrate the flux, that gives us the total flux. So for an elemental area, d phi, which is the elemental flux through that area, because of that area, so d phi will be equal to E dot dA. So delta now becomes d. So d phi is equal to E dot dA, that you can write as E dA cos theta. Now, when this surface area that we are considering is a closed surface. So on the surface starts at one point, then the area spreads in different directions, and ultimately it comes back to the starting point. So it encloses a volume. So the surface is enclosing a volume. So in that case, we call it a closed surface. Then the electric flux out of a closed surface, if the surface is closed surface, then that surface also is called a Gaussian surface. So electric flux out of a closed surface or Gaussian surface can be obtained from the principle that we just discussed, the elemental area. So start with d phi, uh, integrate the d phi over the closed surface. Therefore, phi will be integration of d phi over the closed surface. So, phi is equal to integration of d phi over the closed surface, but d phi is equal to E dot dA. So, phi will be integration of E dot dA over a closed surface. Now, since we have a closed surface, now we can assume that this closed surface, within the surface or in the volume that is enclosed by the surface, there may be charges, there may not be charges. Suppose there is charge Q. If Q is equal to 0, then there is no charge. If Q is not equal to 0, then there is some charge. Suppose the closed surface encloses a charge Q, or encloses total charge enclosed within the closed surface is Q. Then phi, the flux, is proportional to Q, or actually the charge is proportional to the flux. So Q is proportional to phi. If Q is proportional to phi, then we can say Q is equal to epsilon 0 phi. What is epsilon 0? Epsilon 0 is the constant of proportionality. If it is free space, if it is not a dielectric, the volume is not a dielectric, if it is free space, then the constant of proportionality is epsilon 0. So Q is equal to epsilon 0 phi, from which we can say phi is equal to Q upon epsilon 0. Epsilon 0, as you know, is called the permittivity of the free space or dielectric constant of the free space. So phi is equal to Q upon epsilon 0. And now we know two things for closed surface. If the closed surface is enclosing a charge Q or enclosing total charge Q, then phi, which is the flux coming out of the closed surface or flux going into the closed surface, is equal to Q by epsilon 0. So that is one thing that we know. Then by definition of flux, we also know phi is equal to integration of d phi over the closed surface, that is called to E dot dA integrated over the closed surface. So if we equate these two q's, q by epsilon 0 is equal to integration of E dot dA over the closed surface. So integration of E dot dA over the closed surface is equal to q by epsilon 0. This is called the Gauss law, the integral form of the Gauss law. Uh, and the statement of the Gauss law, for this integral form of the Gauss law, the statement is the flux of electric field through a closed surface. Now, the left hand side gives you the flux of the electric field. So E dot dA is the flux of electric field, and that we are evaluating over a closed surface. So the integration is over a closed surface. Therefore, the flux of electric field through a closed surface is proportional to the charge enclosed. Why we say proportional to the charge enclosed? Because that is equal to Q by epsilon 0. Epsilon 0 is a constant, so 1 upon epsilon 0 is a constant. So the flux is equal to a constant into Q. So therefore you can say the flux is proportional to Q. So the flux of electric field through a closed surface is proportional to the charge enclosed. Now let us assume that the surface encloses a volume. So the surface is enclosing a volume. If the surface is enclosing a volume and within the volume the charge per unit volume is rho, or rho is called the charge density, then the total charge within the volume Q, the total charge within the volume is equal to integration of the charge density over elementary volume. So Q is equal to integration rho dV. And so since Q is equal to rho dV, we can now write this Gauss law in integral form in this form. Integration of E dot dA is equal to uh, uh, q by epsilon. Okay, that we'll do later. So integration of E dot dA, that we know from Gauss divergence theorem, divergence of a vector integrated over elementary volume is equal to the well, surface integral of the vector over the surface enclosing the volume. That is what is Gauss divergence theorem. So from Gauss divergence theorem, here the vector is E, and therefore integration of E dot dA is equal to dV integration. And so now integration of E dV is equal to Q by epsilon 0, because integration of E dot dA is equal to Q by epsilon 0, and integration of E dot dA is equal to integration of divergence of E dV. So that you can write. Now Q is equal to integration of rho dV. So on the right hand side we can write as integration of rho dV by epsilon 0. Now on both the sides, left hand side and right hand side, we are integrating over the volume. Therefore the integrands must be same. So therefore divergence of E is equal to rho by epsilon 0. This is again the Gauss law in differential form. So we have seen the Gauss law in integral form and the Gauss law in differential form. Both these forms, integral form and differential form, these are the Gauss law, which are the Maxwell's equation, which is in the differential or integral form. So Maxwell's equation, first law of Maxwell, or first Maxwell's equation is the Gauss law, that is what we say. Now we discussed about closed surface. What happens in the closed surface? The flux coming out of the closed surface or going into the closed surface. Flux can go out or come in. So what will be the electric field can come out of the surface or go into the closed surface. If the electric field is coming out of the surface, then we call the flux is positive. So the flux is positive if the field lines that leave the enclosed volume or through the surface, then the flux is positive. So lines of forces are coming out of the surface. The flux is negative for the field lines that enter the enclosed volume. So if lines of forces are entering the enclosed volume through the surface, then the flux is negative. So flux can be positive or flux can be negative. And how to determine whether it is positive or negative is just look at the field lines If the field lines are coming out of the volume, enclosed volume by the surface, then they are positive. If they are going into the volume, then they are negative. Now suppose a charge is outside a closed surface. If the charge is outside the closed surface, then the net flux is zero. Why the net flux is zero? Because the number of lines of forces that are leaving the surface is equal to the number of lines of surface that are entering the surface. Look at this figure. If you look at this figure, uh, the charge is outside the surface. From the charge, lines of forces are extending to infinity. Now the surface is around the charge. And if you look at the lines of forces, the lines of force, it is a positive charge. So the lines of forces are moving out of the charge. So they are going outward in the outward direction. Now, if you look at the surface or look at the volume, uh, there are two surfaces. One surface is nearer to the charge, other surface is outer, farther from the charge. The surface which is nearer to the charge, and if you look at that, to that surface, the lines of forces are entering. So through those surface, the lines of forces are entering the volume, and the surface which are uh, further from the charge, through those that surface the lines of forces are leaving the volume. So and therefore the number of lines of forces there which are entering, they are equal number of lines of forces are leaving. So as many lines of force enter the surface, same number of lines of force leave the surface. So when the um, charge is outside a volume, enclosed volume, then the net flux from the volume or in the volume is equal to zero. Now let us consider another example. Consider a dipole. We'll consider a dipole. Dipole, as you know, it has equal positive and negative charges. So, positive charges form a pole, negative charges form a pole. So, we consider a dipole. Now, in this dipole, what we'll do is around the positive charges, we'll have a form a surface. Around the negative charges, again we'll have a surface. Um, so this will be surface 1 and surface 2. So imagine two surfaces. One surface is around positive charges, surface 1. One surface is around the negative charges, surface 2. Then in between these two charges, there is another surface. Imagine another surface, which is surface 3. Then imagine a fourth surface which encloses both these all these three surfaces. So both these charges and all these three surfaces, which is S4. So we have four surfaces now. Now, as I told you, S1 encloses the positive charges. Now, since S1 is enclosing the positive charges, therefore, the field everywhere is outward, so flux is positive. So, our flux through S1 is positive since it encloses positive charges. The field is outward through S1, therefore, the flux through S1 is positive here. Similarly, if I look at S2, S2 encloses negative charges. Therefore, the field everywhere is inward towards the negative charge. Therefore, the flux through the surface S2 is negative. Now look at S3. S3 does not enclose any charge. It is between the charge, positive charge and negative charge, but it is not enclosing the positive charge or the negative charge. So S3 does not enclose any charge. Therefore, the number of lines of forces enclosing S3 is same has the number of lines of forces leaving S3. So the flux through this surface is negative in the upper part because it is entering. The flux uh, through the surface S3 is positive in the lower part because it is the lines of forces are leaving, but and they are same. The number of lines of forces entering is same as the number of lines of forces leaving the surface. So since they are same, they will cancel and there will be no net flux through the surface. So through surface S3, there is no net flux. And that is one point. Then we'll come to the surface S4. Surface S4 encloses both the charges, the positive charge and the negative charge. Now, comes the principle. Now comes the main part here. Now S4 has enclosed charges. Since S4 has enclosed charges, so the surface S4 has enclosed charges. The what will be the flux through S4, whether it will be positive, whether it will be negative, or it will be zero. Now here, hence the amount of charges enclosed within S4 is the net amount of charges enclosed within S4 is zero because it encloses positive charges and negative charges which are of same amount of positive charge, same amount of negative charge. So net charge is zero. So there is no net charge enclosed. So since there is no net charge enclosed, the flux are going out and the flux coming in to the surface S4 will be same. So there will be no net flux through the surface S4. So we discussed about uh, the flux and physically how the flux behaves here. And now let us look at an example or an application of Gauss law that we discussed. Let us look at an application of the Gauss law. Remember this thing, the Gauss law is useful only when the electric field is constant on a given surface. Otherwise, the Gauss law is valid everywhere, but it is useful only when the electric field is constant on a given surface. Then we can use the Gauss law properly. Uh, uh, Now, let us consider an infinite sheet of charges, positive charges. If we have an infinite sheet of positive charges, then because the sheet extends, suppose the sheet is in the xz plane, and if the seat is in the xz plane, the electric lines of forces will be always normal to the surface. So they will be always normal to the xz plane, which means the field lines will be in the positive direction or in the negative direction of y. So to the right side of the surface, the electric field will be in the positive direction of y, and to the left side of the surface, the electric field will be in the negative direction of y. But and there will be no electric field in the x direction or z direction in which the surface lies, because electric fields are always normal to the charge. So from the charge they will be normal. Charge is on the surface, therefore they will be always along the positive or negative y direction on this infinite sheet of charges. Now what we will do is we will select a Gaussian surface which is a pillbox. In this case it is a cylindrical pillbox which is passing through this surface with the infinite sheet. So on the pillbox, on the surface, curved surface of the pillbox, there is, if you take normal to the curved surface of the pillbox, the curved surface will be always the normal to the curved surface will be always
either in the xz plane. So it will be in the x-axis or z-axis or in the xz plane. So since it is in the xz plane and electric field is along y direction, so there will be no electric field on the curved surface. No electric field normal to the curved surface. The electric field normal to the curved surface is zero. So there will be no electric field along the curved surface on the cylindrical pillbox. Therefore, and now what is left is that two
ends at the end faces of the cylindrical pillbox. On each pillbox, on each face, the flux will be E into A. So there are two faces, therefore total flux will be phi is equal to 2 times E into A. Flux is E dot A, so on each face it will be E dot A. Now electric field is normal to A, so it will be EA. Cos theta is equal to 0, therefore it will be EA. So for each face it is EA. We have two faces, therefore it will be total will be 2 EA. So phi is equal to 2 EA. Now equate that. So phi is equal to charge enclosed per by epsilon 0. Now phi is equal to 2 EA. So 2 EA is equal to total charge enclosed within the pillbox by epsilon 0. Ah, okay. Since our 2EA is equal to Q enclosed by epsilon 0. So from that we can find out what is E. E will be equal to Q enclosed by 2A into epsilon 0. So just take 2A to the right hand side. So E is equal to Q enclosed by 2A into epsilon 0. Now Q enclosed by A, that gives you the charge per area, charge per unit area. Charge per unit area is called the charge density, surface charge density sigma. Therefore, for a Q enclosed by A, we can write sigma. So E is equal to sigma by 2 epsilon 0, where sigma is equal to Q enclosed per A, that is the surface charge density. Ah, now, from the Gauss law, let us see which is the fundamental law of electricity, which is given by Gauss law, or which is represented by Gauss law. Now what we'll do is integrate the electric flux of a point charge over a spherical Gaussian surface with the charge at its center. So look at the figure. In the figure we are seeing a spherical surface, and at the center of the spherical surface we have a charge, and the sphere is of radius r. The charge enclosed within the sphere at the center, if you assume that all the charge is concentrated at the center, then the charge is a q enclosed, so that is the total charge enclosed at the center. Then the other thing is, from the center electric field lines will come out radially outward. So since they are coming out radially outward on the surface, if you look at the radius, so if you extend the radius through the surface, then the radius is perpendicular to the tangent, where tangent on the surface, where the radius is crossing the surface, that you know. So since the radius is perpendicular to that, therefore E dot dA is equal to EdA. So that you will get. Uh, Now let us look at the Gauss law. Gauss law says that epsilon 0 integration E dot dA, which is the flux, so that is called to epsilon 0. Now E is constant here, because it is coming out with the charge is fixed, so therefore electric lines of forces will be constant, so electric field will be constant. So epsilon 0 into E, then integration of dA. So that is equal to what? If you integrate dA for the sphere. If you have a sphere, integrate dA, which means on the surface area, elementary, if you take elementary area on the surface of the sphere and integrate, you will get the surface area of the sphere. Surface area of the sphere is 4 pi r square. Therefore, epsilon 0 into E into 4 pi r square is the flux, and that is equal to Q by Q enclosed. So epsilon 0, so from Gauss law now we get epsilon 0 E 4 pi r square is equal to Q enclosed. Now solve for E. Find out what is E. E will be equal to Q enclosed by epsilon 0 4 pi r square, that we can write as 1 by 4 pi epsilon 0 into Q enclosed, total charge enclosed, by r square. This is
what is known as Coulomb's law that you have already seen earlier. Hmm, that- so that is what is
Coulomb's law. So E is equal to 1 by 4 pi epsilon 0 Q enclosed by r square is Coulomb's law, which means Gauss law and Coulomb's law both are one and same thing. So from Gauss law you can derive Coulomb's law. From Coulomb's law also you can derive Gauss law. Both the things is possible. Both of them are possible. Either from Coulomb's law you derive Gauss law, or from Gauss law you can derive Coulomb's law. Both of them are possible. Only thing that you should remember is the Gauss law, when you cast Coulomb's law in the form of Gauss law, that becomes very useful under certain circumstances. For example, as we saw on the infinite sheet, so where and there is constant electric field, then the Gauss law is useful. Coulomb's law is useful everywhere. Gauss law is useful under special circumstances. So if you, instead of Coulomb's law, if you want to use Gauss law, you should have special circumstances. There should be symmetry. Under symmetry, Gauss law is more useful. It is easier to apply and get results from Gauss law. Okay. Now let us come to some of the consequences of Gauss law. If we know what is Gauss law,
what are the consequences. So we'll look at
some of the consequences of Gauss law. So
before that maybe we can take a break of 5 minutes and I'll come back after 5 minutes and look at the consequences of those.